What is the 3W principle of PCB routing? When designing PCBs, we often talk about the 3W principle, which refers to two PCB traces, where the distance between their centers is not less than 3 times the trace width. This W refers to the width of the PCB trace. The purpose of this is to reduce crosstalk between two traces. Generally, clock signals, reset signals, or some key signals need to follow the 3W principle. When the 3W principle is met, crosstalk between traces can be reduced by 70%, and if it is 10W, crosstalk can be reduced by 95%. The 3W principle is conditional and is also related to the distance between the trace and the reference plane. For example, for a 4-layer or 6-layer board, the distance between the trace and the reference plane is generally about 5 mm. Following the 3W principle for routing can effectively avoid crosstalk. However, if it is a 2-layer board, the distance between the trace and the reference plane may be 50 mm. In order to effectively reduce crosstalk, the distance between traces may need to be greater than 3W. When evaluating crosstalk in PCB routing, we generally refer to the coupling coefficient parameter. The larger the coupling coefficient, the more likely crosstalk will occur between PCB traces. Of course, crosstalk is also related to the coupling length between traces and the frequency of signals. We simulated a 6-layer board and a 2-layer board PCB trace coupling situation using software. The PCB trace width was 5 mm and the center distances were 25 mm, 15 mm, and 10 mm respectively. The signal rise time was chosen as 100 ps. Let's take a look at the simulation results. When the distance between traces on a 6-layer board is 25 mm, that is, when the center distance is 5W, the coupling coefficient is 1.9, which is relatively small, and we consider this trace to be okay. When the distance between traces is 15 mm, that is, when the center distance is 3W, the coupling coefficient is 5 and we consider this trace to be okay as well. Generally, when we do PCB trace coupling simulation, a coupling coefficient of 5% is a critical value. If it is less than 5%, we consider that trace to be okay. If it is greater than 5%, we may need to adjust the distance between traces. When the distance is 10 mm, that is when the center distance is 2W, then coupling coefficient becomes 9.8 and we consider that there's a risk of crosstalk occurring in this trace and that we need to adjust its spacing. Now let's take a look at when spacing on a 2-layer board becomes 25 mm, then coupling coefficient becomes 17.6, when spacing becomes 3W, then coupling coefficient becomes 23.7, when spacing becomes 2W, then coupling coefficient becomes 28.8. For these spacings on a 2-layer board, all coupling coefficients are greater than 5%. Just like what we said earlier, in order to effectively reduce signal crosstalk, key signal trace spacing on a 2-layer board generally needs to be greater than 3W.